Many explanations in physics begin with a familiar claim. The universe moves toward lower energy. Iron rusts because free energy drops. Hot objects cool. Chemical reactions settle into more stable states. But when we enter the world of particles, that comfortable rule begins to crack. Neutrinos appear almost exclusively left-handed, even though left and right carry the same energy. So what is really guiding the laws of nature, energy efficiency, or something deeper embedded in the structure of the Standard Model? Tonight we step into that puzzle, beginning with, does the universe really choose lower energy? Or is that a comforting myth? If the universe truly preferred lower energy in every situation, then a troubling inconsistency would appear immediately. A neutrino moving through space could rotate its orientation from left to right without changing its energy at all. And yet, in the real world of particle experiments, neutrinos consistently reveal themselves with a left-handed orientation when they interact through the weak force. This small detail, almost invisible in everyday life, opens a doorway into one of the most subtle misunderstandings in physics: the belief that nature always chooses the lowest possible energy state. Many scientific explanations begin with a familiar story drawn from thermodynamics. A system evolves toward a configuration that lowers its energy. A stretched spring relaxes. A hot object cools. Chemical reactions proceed towards stability. These examples are accurate, but the deeper rule is more precise than the phrase, energy decreases. What actually governs spontaneous processes is a quantity called Gibbs free energy, which combines energy with entropy, the measure of how many microscopic arrangements are available to the system. This distinction was clarified during the 19th century by the American physicist Josiah Willard Gibbs, whose work quietly reshaped chemistry and thermodynamics. Gibbs introduced a framework describing how systems evolve under constant temperature and pressure, conditions that match most processes occurring on Earth. In this framework, the decisive quantity is G equals H minus T times S, where H represents enthalpy, T temperature, and S entropy. When the change in Gibbs free energy becomes negative, the transformation proceeds naturally because the final arrangement is statistically more favorable. One of the most familiar demonstrations of this principle appears in the slow formation of rust. Iron atoms arranged in a metallic lattice are relatively ordered. When exposed to oxygen and moisture, they react to form iron oxides. During this transformation, energy is released while the microscopic configurations available to the atoms increase. Both effects reduce the Gibbs free energy of the system. Measurements confirm this thermodynamic direction with impressive precision. The formation of iron, 3, oxide from iron and oxygen, produces a Gibbs-free energy change of roughly -740 kilojoules per mole at standard conditions. Engineers cannot reverse that thermodynamic tendency without expending additional energy, which is why bridges, pipelines, and ships require coatings or alloying elements to slow corrosion. From the perspective of chemistry, the phrase "nature prefers lower energy" appears reasonable because many everyday processes follow the same pattern. Combustion reactions release heat. Crystals form from solutions. Metals oxidize. Yet the phrase becomes misleading when applied outside the domain of thermodynamics, especially when we move into the microscopic world of elementary particles. Particles do not evolve toward equilibrium states in the same statistical way that atoms in a chemical reaction do. Instead, they interact according to rules encoded in quantum fields and symmetry structures. These rules determine which particles can interact, which transformations are allowed, and which interactions are forbidden entirely. The neutrino illustrates this difference with remarkable clarity. The particle was first proposed in 1930 by Wolfgang Pauli to account for missing energy in beta decay. Radioactive nuclei were emitting electrons with a range of energies that did not match simple conservation laws. Pauli suggested that an unseen particle carried away the missing momentum. He wrote in a famous letter to colleagues, "I have done a terrible thing. I have postulated a particle that cannot be detected." For many years, the neutrino remained hypothetical. Detection finally occurred in 1956, when Frederick Rines and Clyde Cowan observed antineutrinos emitted from a nuclear reactor in South Carolina. Their detector relied on a rare reaction in which an antineutrino interacts with a proton, producing a positron and a neutron. The signal appeared as two flashes of light separated by a short delay, a distinctive signature confirming the particle's existence. Today, neutrinos are known to be among the most abundant particles in the universe. Inside the Sun, nuclear fusion converts hydrogen into helium, producing neutrinos in the process. Roughly 60 billion solar neutrinos pass through each square centimeter of Earth every second. They interact so weakly with matter that nearly all of them pass through the entire planet without leaving a trace. To detect even a small fraction of these particles, physicists have constructed enormous observatories. The Super Kamiokande detector in Japan contains 50,000 tons of ultra-pure water surrounded by thousands of light sensors. When a neutrino interacts with an electron or nucleus in the water, the resulting particle emits a faint cone of Cherenkov radiation that reveals the neutrino's direction and energy. Another example is the Ice Cube Neutrino Observatory at the South Pole. Instead of water tanks, Ice Cube uses the Antarctic ice sheet itself as the detection medium. More than 5,000 optical sensors are embedded deep in the ice over a cubic kilometer of volume. These detectors capture flashes of light produced when extremely energetic neutrinos interact with atomic nuclei in the ice. Such experiments have established several key properties of neutrinos. One of the most surprising discoveries came in the late 1990s, when observations from Super Kamiokande demonstrated that neutrinos oscillate between different types, electron, muon, and tau neutrinos while traveling through space. Oscillation requires mass, meaning neutrinos are not exactly massless, as originally assumed in the Standard Model. Within these measurements lies the pattern that concerns us here. When neutrinos interact through the weak force, their orientation consistently appears left-handed. In simple language, the particle's spin points opposite to its direction of motion. This feature might seem minor, but it carries profound implications. If energy minimization controlled the process, both orientations would appear equally because spin orientation does not alter the particle's kinetic energy. The energy of a relativistic particle depends primarily on its momentum and mass through the relation E squared equals P squared times C squared plus M squared times C to the fourth. Spin direction relative to motion does not appear in that equation. The explanation lies not in thermodynamics, but in the architecture of the electroweak interaction, the unified description of electromagnetic and weak forces developed during the 1960s. Physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg constructed a theory based on gauge symmetry known as SU2 times U1. Within this structure, Particles are arranged into mathematical groupings that determine how they interact with the W and Z bosons. In this framework, left-handed fermions belong to SU2 doublets, while right-handed versions are placed in singlets that do not couple to the charged W boson. Because of this arrangement, the weak force interacts only with left chiral fields. The handedness observed in neutrino interactions is therefore not a matter of energy preference. It is a structural feature of the theory itself. Experimental evidence for this asymmetry arrived dramatically in 1957 through the work of Chien-Shiung Wu and her collaborators. Their experiment used cobalt-60 nuclei cooled to extremely low temperatures and placed in a strong magnetic field so that nuclear spins aligned in the same direction. When the nuclei underwent beta decay, the emitted electrons showed a clear directional preference relative to the spin orientation. If mirror symmetry held, electrons would emerge equally in both directions. Instead, they favored one orientation, demonstrating that the weak interaction violates parity symmetry. The result shocked the physics community, because parity had long been assumed to be a universal law of nature. Physicist Wolfgang Pauli later expressed his disbelief with characteristic humor, remarking, "I cannot believe that God is a weak left-hander." The experiment revealed that the weak force distinguishes between left and right in a fundamental way. This property is woven into the structure of the interaction itself, not produced by an energetic advantage. Seen from a wider perspective, the comparison between rust and neutrinos illustrates two different layers of physical law. Rust formation belongs to thermodynamics and statistical mechanics, where entropy and energy together determine the direction of change. Neutrino-handedness belongs to the symmetry structure of quantum field theory, where interactions are determined by gauge charges and coupling rules. These two frameworks operate simultaneously in the universe but govern different phenomena. Chemical reactions in stars, planetary atmospheres, and biological systems follow thermodynamic principles. Particle interactions inside atomic nuclei follow quantum field theory. Confusing the two can lead to explanations that sound plausible yet fail under closer examination. A small puzzle often comes up when this idea is first discussed. If left and right-handed orientations carry exactly the same energy, why does the weak force consistently interact with only one of them? And why do many simplified explanations still describe this pattern as if nature had simply chosen the more energy-efficient option? The explanation becomes clearer once we separate two ideas that are frequently mixed together in popular discussions: the thermodynamic tendency of systems to lower their free energy, and the symmetry rules that govern particle interactions in the Standard Model. If left and right don't change energy, why do people keep saying they do? What if one of the most common explanations repeated in classrooms and documentaries rests on a quiet misunderstanding, a habit of borrowing intuition from chemistry and applying it to a domain where those rules no longer govern? The idea that left-handed neutrinos exist because the universe prefers lower energy appears persuasive at first glance. It echoes the thermodynamic language used to explain rust, chemical reactions, and the cooling of hot objects. Yet when physicists examine the mathematics and the experiments that reveal the behavior of neutrinos, that explanation begins to dissolve. The difference between left and right in particle physics is not an energy difference at all. It is something more subtle, something tied to the geometry of motion and spin. To see why the confusion persists, it helps to begin with a pattern the human mind finds comforting. Many physical processes appear to move toward stability. A compressed gas expands when allowed. Heat flows from a hotter body to a cooler one. Iron slowly transforms into rust when oxygen and water are present. These processes are explained through thermodynamics, where the relevant quantity is free energy, a balance between energy and entropy. In that domain, the language of preference makes sense because large collections of atoms explore many microscopic arrangements and settle into the statistically favored configuration. When such language migrates into particle physics, it creates a misleading picture. Neutrinos do not participate in thermodynamic equilibrium in the same way that atoms in a chemical reaction do. Instead, they belong to the framework of quantum field theory. In that framework, each particle is an excitation of an underlying field that fills space. The properties of the particle arise from how the field transforms under symmetries of spacetime and under internal symmetries that define the fundamental forces. These rules were established through decades of experiment and theoretical work, culminating in what physicists call the Standard Model. Within this framework, the energy carried by a particle depends on two quantities that experiments can measure with extraordinary precision. One is mass. The other is momentum, which describes how fast the particle moves and in which direction. These quantities determine the particle's total energy through a relation first clarified in the theory of relativity developed by Albert Einstein in the early 20th century. In everyday language, the relation says that a particle's energy grows when its motion becomes faster or when its mass becomes larger. The orientation of the particle's spin relative to its motion does not appear as an independent contribution to that energy. Spin is a fundamental property of particles, discovered during the early development of quantum mechanics. In 1925, George Uhlenbeck and Samuel Gaudsmit proposed that electrons behave as though they possess an intrinsic angular momentum. The concept quickly became central to atomic physics because it explained fine details in the spectra of atoms. Every known fermion, including electrons, quarks, and neutrinos, carries spin equal to 1/2 in natural units. That property does not mean the particle literally rotates like a tiny sphere. Instead, it describes how the particle responds to rotations of space itself. Now imagine a particle traveling through space while possessing this intrinsic spin. The spin can point in a direction either aligned with the motion or opposite to it. Physicists call this relationship helicity. If the spin points along the direction of motion, the particle is described as right-handed. If the spin points opposite the direction of motion, the particle is described as left-handed. The labels arise from a geometric picture. If you extend the thumb of your right hand along the direction of motion and curl your fingers in the direction of the spin, the orientation matches the definition of right-handed helicity. Reverse the relation and the configuration becomes left-handed. At this stage, the concept is purely geometric. Nothing in the definition implies a difference in energy. A particle moving with a certain momentum will have the same energy whether its spin points forward or backward relative to its motion. In fact, experiments confirm this symmetry in many contexts. Electrons produced in accelerators can appear in either helicity state, and both carry identical kinetic energy when their momentum is the same. So, where did the idea arise that neutrinos might behave differently because of energy considerations? The answer lies partly in the language used to introduce quantum physics to students. Analogies drawn from thermodynamics are easy to visualize. Teachers often describe systems settling into lower energy states because it resembles familiar experiences. When that language migrates into discussions of fundamental particles, it can blur the distinction between statistical behavior and interaction rules. The turning point came in the 1950s when physicists began to examine the symmetry properties of the weak nuclear force. At that time, parity symmetry, the idea that the laws of physics remain unchanged under mirror reflection, was widely believed to be universal. The expectation was simple. If one constructed a mirror image of any physical process, the mirror version should obey the same laws. Yet a few puzzling experimental results in beta decay suggested that the weak interaction might not respect this symmetry. Two theoretical physicists, Sung-Dao Lee and Chien-Shiung Yang, examined the available data in 1956. They realized that no decisive experiment had ever tested parity symmetry in weak interactions. Their analysis suggested that parity might be violated. If that were true, processes mediated by the weak force would distinguish between left and right orientations. The proposal challenged a long-held assumption about the symmetry of nature. Chien-Shiung Wu and her collaborators designed the experiment that would test the idea. They used nuclei of cobalt-60, cooled to extremely low temperatures and placed within a strong magnetic field so that the spins of the nuclei aligned in a common direction. When these nuclei underwent beta decay, they emitted electrons. If parity symmetry held, the electrons would be emitted equally in directions parallel and anti-parallel to the nuclear spin. The experiment revealed something different. The electrons emerged preferentially in one direction relative to the spin orientation. The mirror image of the process would not match the real one. The result demonstrated that the weak force distinguishes between left and right. Parity symmetry was broken in weak interactions. The discovery shocked the physics community and earned Sung-Dao Lee and Chien-Shiung Yang the Nobel Prize in Physics in 1957. The experiment also revealed that the weak interaction couples strongly to particles with a particular handedness. Electrons produced in beta decay tended to emerge with left-handed helicity. Neutrinos provided an even clearer case. When neutrinos participate in weak interactions, they appear overwhelmingly in a left-handed state. Their antiparticles, antineutrinos, appear predominantly right-handed. The pattern does not arise because one orientation carries less energy than the other. Instead, it arises because the weak interaction couples only to specific chiral components of fermion fields. The equations of the Standard Model include this asymmetry from the start. The distinction between helicity and chirality becomes important here. Helicity describes the geometric relation between spin and motion. Chirality refers to how a particle transforms under the mathematical symmetries of the electroweak theory. For particles with zero mass, the two concepts coincide. For particles with non-zero mass, they can differ, because observers moving at different velocities can see helicity reversed. Neutrinos were once thought to be massless, which made the left-handed pattern appear absolute. Later experiments revealed that neutrinos possess a small mass and can oscillate between different types. Even so, the weak interaction still couples only to the left chiral component. The measurement of neutrino oscillations came from several experiments during the late 20th and early 21st centuries. The Super Kamiokande detector in Japan observed atmospheric neutrinos produced when cosmic rays strike the upper atmosphere. The Sudbury Neutrino Observatory in Canada measured neutrinos arriving from nuclear reactions inside the Sun. Both experiments confirmed that neutrinos change flavor as they travel. This phenomenon requires that neutrinos possess mass, although the mass is extremely small, less than a few tenths of an electron volt. These discoveries illustrate a broader lesson. The behavior of elementary particles is governed not by thermodynamic preferences, but by the symmetry structure of the quantum fields that define the fundamental forces. The weak interaction couples only to left chiral fermions, because that is how the gauge symmetry of the electroweak theory organizes the fields. Experiments from nuclear decay to high-energy collisions confirm the prediction again and again. The confusion between energy preference and symmetry structure persists because human intuition gravitates towards simple narratives. Lower energy states provide a clear mental image. Symmetry groups and quantum fields require a more careful picture. Yet the evidence gathered over decades of experiment leaves little ambiguity about which framework describes neutrino interactions. One of the most respected voices in science communication, Carl Sagan, often reminded audiences that science advances by replacing comforting stories with explanations grounded in observation. In his words, extraordinary claims require extraordinary evidence. The handedness of neutrinos is not an extraordinary claim today because the evidence has accumulated across generations of experiments. What remains extraordinary is how a subtle property of spin and motion can reveal the deep symmetry structure of the laws governing matter. A remaining tension still sits within this picture. If helicity alone does not determine how neutrinos interact, and if chirality is the property that the weak force actually couples to, then the distinction between these concepts becomes essential. The structure of the electroweak theory allows only left chiral neutrinos to interact through the W boson. That rule appears directly inside the equations of the Standard Model. At that point, the meaning of the word left-handed itself becomes crucial. In different contexts, the term may refer to spin, helicity, or chirality, and those ideas are related but not identical. What exactly is left-handed, spin, helicity, or something even stranger? Imagine a particle so small that trillions of them pass through your body every second, moving close to the speed of light, almost never interacting with matter, yet carrying within their motion one of the most revealing clues about how the universe organizes its fundamental forces. Now imagine pursuing that particle through space, accelerating faster and faster until your motion nearly matches its own. In that moving frame of reference, something remarkable can happen. The orientation we once described as left-handed may appear reversed. A property that seemed absolute begins to depend on motion itself. The natural reaction is immediate. If that reversal occurs, would the weak interaction suddenly stop recognizing the particle? To understand why this situation unfolds the way it does, the discussion must begin with the physical meaning of spin. In quantum theory, every fermion carries an intrinsic angular momentum known as spin equal to 1/2. This quantity behaves mathematically like the angular momentum of a rotating object, although the particle itself is not literally spinning like a tiny sphere. Instead, spin describes how the particle responds when space is rotated. Experiments using magnetic fields confirm this behavior. When particles such as electrons pass through a non-uniform magnetic field, their trajectories separate according to the orientation of their spin, a phenomenon first observed in the Stern and Gerlach experiment conducted in 1922. Spin alone does not yet tell us what physicists mean by handedness. That concept emerges when spin is compared with the direction of motion. If the spin vector points along the same direction in which the particle travels, physicists describe the particle as having right-handed helicity. If the spin points opposite to the direction of motion, the particle possesses left-handed helicity. The definition is geometric. A particle moving north while its spin points north is right-handed. If the spin points south while the particle moves north, it becomes left-handed. Helicity can therefore be understood as a relationship between two vectors. One represents the particle's motion through space. The other represents its intrinsic angular momentum. For particles that travel much slower than the speed of light, helicity can easily be reversed simply by observing the particle from a reference frame moving faster than the particle itself. In that new frame, the particle's direction of motion appears reversed, while the orientation of the spin remains unchanged. The relation between spin and motion flips, and the helicity changes sign. This thought experiment becomes especially interesting for neutrinos because these particles travel extraordinarily close to the speed of light. Neutrinos are produced in nuclear reactions, including those occurring inside stars and inside nuclear reactors on Earth. Measurements from the Super Kamiokande detector in Japan and the Sudbury Neutrino Observatory in Canada reveal that solar neutrinos typically carry energies of several mega-electron volts while their masses are extremely small. Modern neutrino experiments constrain the sum of neutrino masses to less than about 0.12 electron volts. The difference between energy and mass is therefore enormous. Because of this enormous ratio between energy and mass, neutrinos move with velocities extremely close to the speed of light. To overtake such a particle would require an observer traveling even faster, which is impossible for any object with mass according to the theory of relativity established by Albert Einstein in 1905. The thought experiment remains useful because it clarifies a crucial point. Helicity depends on motion. Chirality does not. Chirality arises from the mathematical structure of quantum field theory. In the standard model of particle physics, fermions are described by spinor fields that can be separated into two components. One component transforms in a way that physicists label left chiral. The other transforms as right chiral. These labels do not refer to geometric orientation alone. They describe how the field behaves under Lorentz transformations, the symmetry operations associated with space and time in relativity. When neutrinos interact through the weak force, the interaction couples only to the left chiral component of the neutrino field. This rule appears directly in the equations describing the electroweak interaction developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg during the 1960s. Their theoretical framework unified the weak nuclear force with electromagnetism and predicted the existence of the W and Z bosons. Particles later observed at the European Organization for Nuclear Research in 1983. In the electroweak theory, the weak interaction distinguishes between left and right chiral fields. Left chiral fermions participate in the charged current interaction mediated by the W boson. Right chiral fermions do not. This asymmetry explains why neutrinos observed in weak processes overwhelmingly appear with left-handed helicity. The weak force does not respond to helicity directly. It responds to chirality. The difference becomes clear when considering particles that possess mass. For a massless particle, helicity and chirality coincide. The two concepts become identical because the particle always travels at the speed of light and no observer can reverse its direction of motion. For a particle with mass, even a very small mass, the situation changes. The particle's quantum state contains a mixture of helicity components, although one component may dominate strongly. Neutrinos fall precisely into this category. Experiments conducted during the late 20th century demonstrated that neutrinos possess a small but non-zero mass. Evidence came from the observation of neutrino oscillations, a phenomenon in which neutrinos produced with one identity later appear as another. The discovery required detectors capable of observing extremely rare interactions. The Sudbury Neutrino Observatory used 1,000 tons of heavy water placed deep underground in Canada to shield the detector from cosmic radiation. Measurements performed in 2001 confirmed that neutrinos arriving from the Sun transform among 3 different types during their journey to Earth. The existence of mass means that a neutrino state is not purely one helicity configuration. Instead, the particle's quantum description contains a dominant helicity aligned with the weak interaction, along with a suppressed component carrying the opposite orientation. The strength of that suppressed component depends on the ratio between the neutrino's mass and its energy. When the energy greatly exceeds the mass, the opposite helicity component becomes extremely small. This relationship explains why neutrinos produced in high-energy processes appear almost entirely left-handed. Consider a neutrino produced in a nuclear reaction with energy of several mega-electronvolts. Its mass may be less than 1 electronvolt. The ratio between these quantities is therefore smaller than 1 part in a million. The probability of observing the opposite helicity component becomes correspondingly tiny. Experiments therefore detect neutrinos that appear purely left-handed, even though the underlying quantum description allows a minute admixture of the opposite orientation. The insight illustrates an important pattern in physics. Observations often reflect an approximation that becomes extraordinarily accurate within certain energy ranges. In the early decades of neutrino research, physicists believed neutrinos were exactly massless. The assumption simplified calculations and matched experimental data available at the time. Later measurements refined that picture. The discovery of neutrino oscillations demonstrated that neutrinos possess mass after all, though the value remains extremely small. The story of neutrino mass itself carries an intriguing historical thread. Wolfgang Pauli first proposed the neutrino in 1930 to explain missing energy in beta decay experiments. Pauli wrote a famous letter to colleagues beginning with the words, "I have done a terrible thing. I have postulated a particle that cannot be detected." For more than 2 decades, the particle remained hypothetical. In 1956, Clyde Cowan and Frederick Rines confirmed its existence through experiments conducted near a nuclear reactor in the United States. Their detector captured the faint signal produced when antineutrinos interacted with protons in water. Decades later, increasingly sensitive detectors transformed neutrino physics into one of the most precise frontiers of particle research. Instruments buried deep underground or placed within Antarctic ice monitor flashes of light produced when neutrinos interact with surrounding matter. The IceCube Neutrino Observatory at the geographic South Pole contains more than 5,000 optical sensors embedded within a cubic kilometer of ice. These sensors record Cherenkov radiation emitted by charged particles created in neutrino interactions. Such experiments reveal that neutrinos travel vast distances across the universe almost without obstruction. Neutrinos produced in the Sun reach Earth in about 8 minutes. Others arrive from distant supernova explosions and from energetic astrophysical sources billions of light-years away. Despite this immense journey, their internal quantum properties remain governed by the same principles of helicity and chirality that define their interactions at the smallest scales. The distinction between helicity and chirality, therefore, resolves the puzzle posed at the beginning of this exploration. A neutrino's helicity may appear different to observers moving at different velocities, yet the chirality that determines weak interactions remains fixed within the particle's quantum field. The weak force continues to interact with the left chiral component regardless of how an observer interprets the geometric orientation of spin and motion. One more detail still stands out in this picture. The Standard Model contains this asymmetry as a fundamental rule. The equations treat left chiral fermions and right chiral fermions differently. Experimental results confirm that rule with remarkable precision. Yet the deeper origin of this asymmetry is still not fully understood. Within electroweak theory, even the carriers of the weak force follow the same chiral preference. At that point, the interaction carrier itself comes into focus. The W boson in the exploration. Why does the W boson only talk to left chiral particles? Why would one of the universe's fundamental forces follow a rule that appears so strangely selective, interacting only with particles of a particular handedness, as though nature itself had built a lock that accepts only one orientation of key? The answer lies deep inside the architecture of the Standard Model of particle physics, a theoretical framework constructed through decades of experiment and refined mathematical insight. Within this framework, the weak interaction does not merely happen to favor left chiral particles. Its structure is built in such a way that only those particles participate in the interaction mediated by the W boson. What appears at first like a curious preference turns out to be a direct consequence of how the fundamental fields of nature are organized. The story begins during the middle decades of the 20th century, when physicists were trying to understand how the weak nuclear force fits alongside the other known forces. The weak interaction had already been recognized through its role in radioactive beta decay, a process in which a neutron transforms into a proton while emitting an electron and an antineutrino. Experiments studying beta decay revealed patterns that did not resemble the symmetry properties familiar from electromagnetism. In 1957, the work of Chien-Shiung Wu demonstrated that weak interactions violate mirror symmetry. This discovery forced physicists to reconsider the mathematical structure underlying the force itself. In the years that followed, theorists began building a unified description of the weak and electromagnetic interactions. The breakthrough came through the independent work of Sheldon Glashow, Abdus Salam, and Steven Weinberg. Their framework, now known as electroweak theory, proposed that the weak and electromagnetic forces arise from a single-gauge symmetry that becomes separated only after the universe cooled during the earliest fractions of a second following the Big Bang. Experiments later confirmed this idea with extraordinary precision, particularly after the discovery of the W and Z bosons at the European Organization for Nuclear Research in 1983. To understand why the W boson interacts only with left chiral particles, one must look carefully at how fermions are arranged within this theory. Fermions are the particles that make up matter. They include electrons, neutrinos, and quarks. In the electroweak framework, these particles are not simply listed as individual entities. Instead, they are grouped into mathematical pairs known as doublets. Each doublet contains two related particles that transform together under the symmetry governing the weak interaction. For example, the electron and the electron neutrino form one such pair. These two particles appear side by side within a structure called an SU2 doublet. The letters SU refer to a mathematical symmetry group describing how fields transform when certain rotations occur within an abstract internal space. The number 2 indicates that the doublet contains two components. When the symmetry operation acts on the doublet, the electron and the neutrino transform into combinations of each other. This arrangement has a remarkable implication. Only the left chiral components of these fermion fields appear within the SU2 doublets. The right chiral components do not join the pair. Instead, they stand alone as singlets, objects that remain unaffected by the symmetry operations associated with the weak interaction. Because the W boson couples directly to the SU2 doublets, it interacts only with those left chiral fields contained within them. The distinction may sound abstract at first, yet experiments confirm it again and again. When a neutron decays into a proton, the process proceeds through the emission of a W boson. That boson then converts into an electron and an antineutrino. Measurements of the angular distributions of the emitted particles reveal a clear pattern. The electron emerges with a preference linked to left chiral coupling. This behavior matches the predictions of the electroweak theory with remarkable precision. The strength of this coupling has been measured in particle accelerators across the world. At the European Organization for Nuclear Research, high-energy proton collisions produce W bosons whose mass is approximately 80,000 megaelectron volts. These particles exist only for a fleeting moment before decaying into lighter particles such as electrons, muons, and neutrinos. Detectors track the resulting particle trajectories and measure the energies involved. The patterns observed in those decays confirm that the W boson interacts only with left chiral fermions. One of the striking aspects of this discovery is how deeply it connects the behavior of elementary particles with the structure of mathematical symmetry. In many areas of physics, symmetry principles serve as guiding rules that restrict what interactions can occur. Electromagnetism arises from a symmetry known as U one-gauge invariance. The strong nuclear force emerges from a symmetry called SU3, associated with quantum chromodynamics. The weak interaction combined with electromagnetism originates from a symmetry structure involving SU2 together with U1. Within that structure, the left chiral doublets occupy a privileged position. They are the entities that transform under the SU2 symmetry. Because the W boson itself is a carrier of this symmetry, it naturally couples to those doublets. Right chiral fermions, lacking membership in the doublet, remain invisible to that particular interaction channel. This is not a matter of energy preference or energetic efficiency. It is a consequence of how the underlying fields are arranged within the symmetry group governing the interaction. Historical context adds depth to this picture. When Steven Weinberg published his electroweak model in 1967, the idea that symmetry principles could determine the existence and properties of new particles was still gaining acceptance. The model predicted not only the W boson, but also a neutral partner known as the Z boson. For many years, these particles remained theoretical constructs. Their eventual discovery at the European Organization for Nuclear Research transformed the model from speculation into established physics. Carlo Rubbia and Simon van der Meer led the experiments that detected these bosons using the superproton synchrotron accelerator. The observation earned them the Nobel Prize in Physics in 1984. The measured properties of the W and Z bosons matched the predictions of electroweak theory with striking accuracy, including the chiral structure of their interactions. Another crucial component of this framework involves the Higgs field, discovered experimentally at the Large Hadron Collider in 2012. The Higgs field permeates all of space and provides mass to many elementary particles through their interaction with it. While the Higgs mechanism explains how particles acquire mass, it does not alter the chiral structure of the weak interaction. Left chiral fermions remain members of the SU2 doublets even after mass emerges through the Higgs field. The experimental reach of modern particle physics continues to test these ideas in extraordinary detail. The Large Hadron Collider accelerates protons to energies exceeding 6,000 giga-electron-volts before colliding them. Detectors such as ATLAS and compact muon solenoid analyze the resulting particle showers with millions of electronic channels. Among the countless events recorded each year, physicists examine the decay patterns of W bosons to verify that the interaction remains strictly left chiral. Neutrino experiments also contribute to this picture. Facilities such as the IceCube Neutrino Observatory at the geographic South Pole detect neutrinos arriving from astrophysical sources. Although these detectors focus primarily on neutrino interactions with matter, their measurements remain consistent with the same electroweak coupling rules established in accelerator experiments. Even neutrinos traveling across billions of light-years still interact according to the left chiral structure predicted by the Standard Model. Carl Sagan once remarked that science is a way of thinking much more than it is a body of knowledge. The electroweak theory illustrates this idea clearly. The behavior of the W boson does not emerge from guesswork or metaphor. It follows from a logical structure in which symmetry determines the allowed interactions between fields. Observations from nuclear decay, accelerator experiments, and neutrino detectors all reinforce the same conclusion. Yet, the structure leaves an intriguing opening. Right chiral neutrinos do not participate in the SU2 doublets of the Standard Model. Their absence from weak interactions raises an important possibility. Perhaps such particles exist, but remain invisible because they do not couple to the W boson or to the Z boson. Theoretical models extending beyond the Standard Model often include these elusive states. If they exist, they may hold clues about how neutrinos acquire mass and how the early universe evolved. This possibility suggests that the asymmetry built into the weak interaction is not merely a mathematical feature of the Standard Model. The equations treat left chiral and right chiral fermions differently, and experiments confirm that nature follows the same rule with remarkable precision. Yet when this pattern first appeared in theoretical work, it challenged a belief physicists had trusted for decades: the assumption that the laws of nature should behave the same way in a mirror. That moment raised a striking historical question. Who first proved that the universe is not mirror, symmetric, and why did the result shock the entire physics community? Imagine constructing a perfect mirror version of the universe, a world in which every particle interaction unfolds exactly as it does here, except that left and right are exchanged everywhere. For decades, physicists believed that such a mirrored universe would obey the same laws of nature as our own. The assumption felt natural because nearly every known force appeared indifferent to left and right. Yet, a single experiment performed during the winter of 1956 revealed something extraordinary. When the weak force governs nuclear decay, the mirror world does not behave the same way. The symmetry breaks. The universe distinguishes between left and right. The roots of this discovery stretch back to the early 20th century, when physicists were assembling the first coherent models of the atomic nucleus. Radioactive decay had already been observed for several decades. Experiments showed that unstable nuclei could transform into new elements while emitting energetic particles. One of the most common forms of this transformation is beta decay, in which a neutron inside the nucleus converts into a proton while emitting an electron and a neutrino. The process revealed that forces operating inside the nucleus could change the identity of fundamental particles. By the 1940s, the weak nuclear force had become recognized as the interaction responsible for this transformation. Yet its mathematical description remained incomplete. Physicists knew that the weak force behaved very differently from electromagnetism or the strong nuclear force. It acted over extremely short distances and allowed particles to change type. Even so, many believed that it still respected the symmetries that governed other interactions. Among those symmetries, parity held a central place. Parity describes the transformation that occurs when spatial coordinates are inverted. In practical terms, it corresponds to replacing a physical system with its mirror image. If parity symmetry holds, the equations describing the system remain unchanged under this reflection. A process observed in ordinary space should proceed identically in its mirror version. The expectation that parity must be conserved felt almost inevitable. After all, the fundamental laws of mechanics, electromagnetism, and quantum mechanics all displayed this symmetry. Physicists had grown accustomed to the idea that nature did not prefer one orientation of space over another. If a process occurred in a laboratory, the mirrored arrangement of the same experiment should yield identical results. Yet during the early 1950s, several puzzling observations began to challenge this assumption. Two theoretical physicists, Sung-Dao Lee and Chien-Shiung Yang, examined the experimental literature on weak interactions and noticed something surprising. No direct test had ever been performed to verify whether parity symmetry truly held in weak processes. The belief that parity must be conserved had become so deeply embedded that few had thought to question it experimentally. Lee and Yang proposed that parity might not be conserved in weak interactions. Their suggestion was bold because it contradicted decades of assumption. If they were correct, certain nuclear decay processes would reveal a preferred orientation in space. In 1956, they published a detailed analysis outlining how such an effect could be detected. Testing the idea required an experiment capable of observing the direction of particles emitted during beta decay relative to the orientation of the decaying nucleus. The physicist who accepted the challenge was Chien-Shiung Wu, one of the most accomplished experimental nuclear physicists of the 20th century. Wu had already earned a reputation for designing meticulous experiments capable of probing subtle effects within atomic nuclei. Wu and her collaborators selected the isotope cobalt-60 for their investigation. This nucleus undergoes beta decay while emitting electrons and antineutrinos. If parity symmetry held, the electrons should be emitted with equal probability in directions aligned with or opposite to the orientation of the nuclear spin. The mirror image of the experiment would produce identical statistics. Creating the necessary conditions required an extraordinary experimental setup. The cobalt-60 sample had to be cooled to extremely low temperatures so that the spins of the nuclei could align with an external magnetic field. Wu's team used liquid helium refrigeration techniques to reach temperatures only a few thousandths of a degree above absolute zero, approximately 0.003 Kelvin. At such temperatures, thermal motion becomes minimal, and the nuclei align with the applied magnetic field, producing a well-defined orientation for the experiment. With the nuclear spins aligned, detectors measured the directions in which electrons were emitted during beta decay. The expectation under parity symmetry was straightforward. Half the electrons should travel in the direction of the nuclear spin, and half should move opposite to it. The mirror version of the experiment would look exactly the same. The results told a different story. The electrons emerged predominantly in one direction relative to the spin orientation. Instead of displaying perfect symmetry, the decay process showed a clear preference. The mirror image of the experiment would not produce the same outcome. Parity symmetry had been violated. The discovery stunned the physics community. For decades, parity had been treated as an unquestioned principle of nature. The Wu experiment demonstrated that one of the fundamental forces breaks this symmetry completely. The weak interaction distinguishes between left and right in a way that no other known force does. Further experiments soon confirmed the result. Measurements of muon decay and other weak processes revealed the same asymmetry. The pattern became unmistakable. Whenever the weak force governs a transformation, particles appear with a preferred handedness. Electrons produced in beta decay tend to emerge with left-handed helicity. Antineutrinos appear predominantly with right-handed helicity. The discovery transformed the theoretical understanding of weak interactions. Physicists began constructing models that incorporated this intrinsic asymmetry directly into the mathematical description of the force. These efforts eventually led to the development of the electroweak theory proposed by Sheldon Glashow, Abdus Salam, and Steven Weinberg during the 1960s. In this framework, the weak interaction couples only to left chiral fermion fields, a rule embedded in the symmetry structure of the theory itself. Historical accounts of the Wu experiment often emphasize the remarkable experimental precision required to observe the effect. Aligning nuclear spins at such low temperatures, maintaining stable magnetic fields, and detecting the angular distribution of emitted electrons demanded extraordinary care. The success of the experiment stands as a testament to the ingenuity of Wu and her collaborators. The recognition of this achievement has grown steadily over time. Tsung-Dao Li and Chen-Ning Yang received the Nobel Prize in Physics in 1957 for their theoretical prediction of parity violation. Although Chien-Shiung Wu did not share the prize, historians of science widely regard her experiment as one of the most important demonstrations in modern physics. Beyond its historical significance, the discovery continues to influence contemporary research. The violation of parity symmetry remains a central feature of the weak interaction. Experiments conducted at particle accelerators and neutrino observatories consistently confirm the chiral structure first revealed in the cobalt-60 experiment. Even astrophysical processes reflect this asymmetry. Neutrinos produced in the nuclear reactions that power stars exhibit the same left-handed preference when they interact through the weak force. Observatories detecting neutrinos from the Sun, from supernova explosions, and from high-energy cosmic sources measure interaction patterns consistent with the parity-violating structure established in laboratory experiments. Carl Sagan once observed that, somewhere, something incredible is waiting to be known. The Wu experiment illustrates how an apparently simple question about mirror symmetry opened a path toward deeper understanding of the forces shaping matter. The realization that nature distinguishes between left and right forced physicists to revise their assumptions and construct new theoretical frameworks capable of explaining the phenomenon. The implications extend beyond the laboratory. The asymmetry revealed in weak interactions may have played a role in shaping the evolution of the universe itself. Processes governed by the weak force influence the behavior of neutrinos, the formation of elements in stars, and the balance between matter and antimatter during the earliest moments after the Big Bang. Each of these domains carries traces of the same underlying symmetry breaking discovered in the cobalt-60 experiment. The discovery that the weak interaction violates mirror symmetry forced physicists to reconsider a long-held assumption about how nature organizes its laws. If mirror symmetry does not hold in this domain, then the familiar intuition that physical processes simply settle into the most energy-efficient configuration cannot be the whole explanation. That realization leads directly to a broader question. If it isn't energy optimization, what principle is actually running the show? For generations, people have repeated a familiar phrase about nature. Systems move toward lower energy. Metals rust, hot objects cool, chemical reactions release heat and settle into stable configurations. The pattern appears everywhere in thermodynamics. Yet, when physicists examine the behavior of elementary particles, that comforting rule stops explaining what is happening. The universe does not organize the weak interaction by choosing the cheapest energy configuration. Instead, it follows a stricter rule embedded deep within the mathematical structure of the Standard Model. The decisive factor is not which configuration costs less energy. The decisive factor is which interactions are permitted by gauge symmetry. To appreciate the difference, it helps to recall what thermodynamics actually describes. Thermodynamics deals with enormous numbers of particles interacting within systems that constantly exchange energy and entropy. When iron rusts, atoms of iron combine with oxygen to form iron oxide. The process proceeds because the total free energy of the system decreases when the atoms rearrange into the oxide structure. Entropy also plays a role because many microscopic configurations lead to the rusted state. The final arrangement becomes statistically favored. In that environment, the language of energy preference works well. The system explores countless microstates and gradually settles into one that balances internal energy with entropy. The equations describing these processes involve quantities such as temperature, pressure, and free energy. These concepts explain why chemical reactions proceed spontaneously under certain conditions. The microscopic world of elementary particles follows a different logic. Individual particle interactions do not arise from statistical exploration of many configurations. Instead, they occur through the exchange of force-carrying particles that connect specific quantum fields. The rules governing these exchanges are encoded within gauge symmetries. These symmetries define how the fundamental fields transform when internal rotations occur within abstract mathematical spaces associated with the forces of nature. The Standard Model of particle physics organizes all known elementary particles and interactions within three gauge symmetries. One symmetry governs the strong nuclear force. Another governs the electromagnetic force. The third describes the weak interaction. Each symmetry restricts which particles can interact and how those interactions proceed. The weak interaction operates within a symmetry structure known as SU2 combined with U1. These symbols represent mathematical groups describing how certain internal transformations leave the physical laws unchanged. When the theory was developed during the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, it revealed that particles must be arranged into specific multiplets under this symmetry. Within this arrangement, left chiral fermions appear as doublets under the SU2 symmetry. Each doublet contains two related particles. For example, the electron and the electron neutrino form one such pair. Quarks also appear in similar pairs within the theory. The important point is that the left chiral components of these particles transform together under the SU2 symmetry. Right chiral fermions behave differently. They do not belong to the SU2 doublets. Instead, they appear as singlets under that symmetry, meaning they remain unchanged when the internal transformation acts. Because the W boson itself is associated with the SU2 symmetry, it couples only to the particles contained within the doublets. That structural rule explains why the weak interaction involves only left chiral fermions. The distinction becomes clearer when considering the role of gauge bosons. Gauge bosons are the force carriers that mediate interactions between particles. Photons carry the electromagnetic force. Gluons carry the strong nuclear force. The W and Z bosons carry the weak interaction. Each of these particles arises from the gauge symmetry governing the corresponding force. When a W boson interacts with matter, it connects fields that belong to the SU2 doublets. The interaction changes one member of the doublet into the other. A neutron inside an atomic nucleus illustrates this process. During beta decay, a down quark within the neutron converts into an up quark while emitting a W boson. That W boson then produces an electron and an antineutrino. Every step of this transformation follows the symmetry rules built into the electroweak theory. The W boson couples only to the left chiral quark fields because those are the fields contained within the SU2 doublets. Right chiral quarks remain outside that structure and therefore do not participate in the same interaction channel. Experimental evidence supporting this framework emerged gradually through several generations of particle accelerators. In 1983, researchers at the European Organization for Nuclear Research observed the W and Z bosons directly using the superproton synchrotron. Carlo Rubbia and Simon van der Meer led the teams responsible for detecting these particles. Measurements of their masses and decay patterns matched the predictions of the electroweak theory with striking accuracy. The W boson carries a mass of roughly 80,000 mega-electronvolts. Because of this large mass, the particle exists only briefly before decaying into lighter particles. Detectors surrounding high-energy collisions capture the trajectories and energies of the decay products. These measurements confirm that the W boson interacts only with left chiral fermions. Further tests of the electroweak theory have continued at the Large Hadron Collider. Proton beams circulating in opposite directions collide with energies exceeding several trillion electron volts. Detectors such as ATLAS and compact muon solenoid record the resulting particle showers with extraordinary precision. Among these events, researchers analyze the production and decay of W bosons to verify that the chiral structure predicted by the standard model holds true. The same principles apply to neutrino interactions observed far beyond laboratory accelerators. Neutrinos produced in the Sun through nuclear fusion travel across 150 million kilometers of space before reaching Earth. Observatories such as the Sudbury Neutrino Observatory and Super Kamiokande detect the faint flashes of light produced when these neutrinos interact with atomic nuclei. The interaction rates and angular distributions match the predictions of the electroweak theory. The implication becomes increasingly clear. Thermodynamic processes and particle interactions operate under different organizing principles. In thermodynamics, systems evolve toward configurations that minimize free energy while increasing entropy. In particle physics, interactions occur only when they are permitted by the gauge symmetries and quantum numbers defining the fields. Quantum numbers represent conserved properties associated with these symmetries. Electric charge, weak isospin, and hypercharge all belong to this set. When particles interact, these quantities must remain consistent with the symmetry rules. If an interaction would violate the symmetry constraints, the process simply does not occur. This principle explains why the weak interaction displays its distinctive asymmetry. The preference for left chiral particles does not arise from energetic efficiency. It arises because the gauge symmetry underlying the electroweak force places those particles within the multiplets that the W boson can couple to. Right chiral fermions lack the required transformation properties, so the interaction channel remains closed. The clarity of this structure is one of the achievements of modern particle physics. Over decades of theoretical development and experimental verification, the Standard Model has demonstrated remarkable predictive power. Measurements of particle interactions across many energy scales confirm that the gauge symmetry framework accurately describes the behavior of known elementary particles. Carl Sagan once remarked that science is a way of thinking much more than it is a body of knowledge. The electroweak theory reflects that idea vividly. The theory did not arise from guessing which processes minimize energy. It emerged from the recognition that symmetry principles constrain the possible forms of interaction between fields. Once the structure was written down, experiments confirmed its predictions with impressive precision. Yet the story remains incomplete. The Standard Model describes 3 types of neutrinos and their left chiral interactions with the weak force. It does not include right chiral neutrinos within the SU-2 doublets. Their absence raises a possibility that has intrigued physicists for decades. Such particles might exist, but remain invisible to the weak interaction because they do not carry the appropriate gauge charges. If such states exist, they would interact only through gravity or through new forces beyond the Standard Model. Their presence could help explain the tiny masses of neutrinos and might even influence the evolution of the early universe. That possibility raises a compelling question. Is a right-handed neutrino truly missing, or could it simply be hiding where our current experiments cannot see? What if one of the most elusive particles in the universe has been present all along, moving through detectors, stars, and galaxies without leaving a trace, not because it does not exist, but because the known forces of nature simply do not respond to it? The possibility has occupied physicists for decades. The Standard Model successfully describes 3 types of neutrinos and their interactions through the weak nuclear force. Yet within that framework, something appears incomplete. Only the left chiral neutrino participates in the weak interaction. The mathematical structure of the theory contains no partner carrying right chirality. The absence has prompted a profound and carefully studied possibility. Perhaps the right-handed neutrino exists, but interacts so weakly that current experiments cannot easily detect it. The idea begins with a simple observation about the organization of particles in the Standard Model. Fermions appear in pairs under the electroweak symmetry known as SU2. The electron neutrino and the electron form one such pair. The muon neutrino and the muon form another. Each pair occupies a structure called a doublet. Only the left chiral components of these particles appear within these doublets. The weak interaction mediated by the W boson connects members of these pairs and allows transformations such as neutron beta decay. Right chiral fermions occupy a different position within the theory. The right chiral electron exists, but it appears as a singlet under the SU2 symmetry. It does not participate in the same interaction channel as the left chiral fields. When the Standard Model was formulated in the 1960s, neutrinos were assumed to be massless. Under that assumption, the absence of right-handed neutrinos seemed consistent with experimental evidence. If neutrinos have no mass, a right-handed partner would not be required to construct their equations of motion. Later, discoveries changed that picture. Beginning in the late 20th century, experiments studying neutrinos from the Sun and from cosmic ray interactions revealed that neutrinos oscillate between different identities as they travel. The phenomenon was first observed clearly in measurements made by the Super Kamiokande detector in Japan and later confirmed by the Sudbury Neutrino Observatory in Canada. These experiments demonstrated that neutrinos possess a small but non-zero mass. The existence of mass introduced a new theoretical requirement. In most quantum field theories, a particle with mass involves both left and right chiral components. For electrons and quarks, these components appear explicitly in the Standard Model. For neutrinos, the right chiral component is missing. The simplest way to accommodate neutrino mass would be to introduce a right-handed neutrino field that does not participate in the weak interaction. Such a particle would carry no electric charge, no color charge associated with the strong force, and no weak isospin under the SU2 symmetry. In practical terms, this means that it would not interact through the electromagnetic, strong, or weak forces. Gravity would remain its only guaranteed interaction with ordinary matter. Because the particle lacks the usual weak charge, physicists often refer to it as a sterile neutrino. The word sterile reflects the absence of familiar interactions. Ordinary neutrinos interact through the weak force, although very rarely. A beam of trillions of neutrinos can pass through an entire planet with almost no collisions. A sterile neutrino would interact even less frequently. It would move through detectors almost entirely unnoticed. Despite this near invisibility, sterile neutrinos could still influence measurable phenomena indirectly. If they exist, they might mix with the ordinary neutrino states. In that situation, a neutrino produced in a nuclear reaction could occasionally oscillate into a sterile state while traveling through space. The sterile neutrino would continue moving undetected until oscillating back into an ordinary neutrino that can interact with matter. Physicists search for such effects by examining neutrino oscillation patterns with extreme precision. Experiments measure how the probabilities of detecting different neutrino types change as the particles travel certain distances and energies. Deviations from the predictions of the Standard Model could signal the presence of additional neutrino states beyond the known three. Several experiments have explored this possibility. The liquid scintillator neutrino detector at Los Alamos National Laboratory reported results in the 1990s that hinted at oscillations inconsistent with the three-neutrino framework. Later experiments such as Mini-Boon at Fermi National Accelerator Laboratory investigated similar anomalies. Although the results remain debated, they continue to motivate theoretical studies of sterile neutrinos. Large-scale detectors designed for other purposes also contribute to the search. The IceCube Neutrino Observatory, located at the geographic South Pole Monitors, neutrinos passing through a cubic kilometer of Antarctic ice. Thousands of optical sensors embedded in the ice record flashes of Cherenkov radiation produced when neutrinos interact with atomic nuclei. By analyzing the energy and arrival directions of these events, researchers test whether neutrinos oscillate into invisible sterile states during their journey through Earth. So far, the results have placed increasingly strong limits on how strongly sterile neutrinos could mix with ordinary neutrinos. The absence of clear signals does not eliminate the possibility entirely. Instead, it narrows the range of masses and mixing strengths that remain plausible. Astrophysics offers additional opportunities to probe the existence of sterile neutrinos. In the extremely dense environments inside exploding stars known as supernovae, neutrinos play a central role in transporting energy outward from the collapsing core. If sterile neutrinos exist, they could alter the flow of energy within the explosion. Observations of supernova neutrinos, therefore, provide indirect constraints on their properties. Cosmology also enters the investigation. Measurements of the cosmic microwave background radiation, observed with satellites such as the Planck mission of the European Space Agency, reveal the energy content of the universe during its earliest stages. Additional neutrino species would influence the expansion rate of the young universe and alter the pattern of fluctuations imprinted on the microwave background. Analyses of these observations currently indicate that only 3 light neutrino species contribute significantly to the cosmic radiation density. Even with these constraints, sterile neutrinos remain attractive in theoretical models that extend beyond the standard model. Some versions of the theory suggest that sterile neutrinos could help explain the small masses of ordinary neutrinos through mechanisms that involve very heavy partner particles. Other proposals consider sterile neutrinos as candidates for dark matter, the mysterious substance that appears to make up most of the mass in galaxies and galaxy clusters. The possibility is intriguing because dark matter reveals itself through gravity, but remains invisible to electromagnetic radiation. A sterile neutrino with the right mass and stability could contribute to this unseen matter. Astronomers search for faint X-ray signals that might arise if such particles slowly decay into lighter neutrinos and photons. Observations from space telescopes continue to test these scenarios. The investigation illustrates how a seemingly small gap in a theoretical framework can open entire avenues of research. The absence of right-handed neutrinos from the standard model was once viewed as a minor detail when neutrinos were believed to be massless. The discovery of neutrino mass transformed that detail into a major question about the completeness of the theory. Carl Sagan once reflected that, somewhere, something incredible is waiting to be known. The search for sterile neutrinos embodies that sentiment in a precise scientific sense. The possibility remains open, supported by theoretical motivation, and constrained by an expanding network of experiments. Whether the right-handed neutrino proves to be a real particle or an unnecessary extension of current theory, the search continues to refine our understanding of how neutrinos acquire mass. That puzzle leads directly into another profound line of investigation. If neutrinos possess such tiny masses compared with other particles, the explanation may involve a mechanism connecting them to extremely heavy particles that existed in the earliest moments of cosmic history. And that possibility becomes the focus of the next stage of this exploration through the discussion titled "Could neutrino mass be a fingerprint of heavy right-handed neutrinos?" How can a particle that travels through entire planets almost without interaction possess a mass so small that it is millions of times lighter than an electron, And could that tiny mass be the faint trace of an enormously heavy particle that existed long before the first stars formed? This question has become one of the most compelling lines of investigation in modern particle physics. Neutrinos are astonishingly light. Experiments measuring neutrino oscillations show that their masses are less than a fraction of an electron volt, far smaller than the masses of quarks or charged leptons. The remarkable disparity has encouraged physicists to consider whether the smallness of neutrino mass is not a coincidence, but a consequence of a deeper mechanism connecting neutrinos to particles far heavier than anything we have directly observed. The experimental foundation for this discussion began with the discovery that neutrinos change identity as they travel. When neutrinos are produced inside the Sun through nuclear fusion reactions, they begin their journey toward Earth as electron neutrinos. Yet, detectors on Earth observe that many arrive as muon or tau neutrinos. This phenomenon is known as neutrino oscillation. The first decisive evidence appeared in measurements performed by the Super Kamiokande detector in Japan during the late 1990s. The experiment observed atmospheric neutrinos produced when cosmic rays strike Earth's upper atmosphere. Researchers found that the number of muon neutrinos arriving from certain directions differed from expectations, revealing that neutrinos were transforming into other types during flight. The Sudbury Neutrino Observatory in Canada soon provided a second confirmation. Using 1,000 tons of heavy water buried deep underground to shield the detector from cosmic radiation, the experiment measured neutrinos emitted from nuclear reactions within the Sun. The results showed that the total number of solar neutrinos reaching Earth matched theoretical predictions, yet many arrived in different forms than originally produced. Together, these experiments demonstrated that neutrinos oscillate among three distinct identities. Oscillation requires that neutrinos possess mass, even if that mass is extremely small. Once neutrino mass became established, theorists faced a challenge. In the standard model of particle physics, neutrinos originally appeared as massless particles. The theory contained no explicit right-handed neutrino field to partner with the left-handed neutrino in the way electrons possess both chiral components. Adding such a partner immediately raised another puzzle. If neutrinos have both left and right components, like other fermions, why are their masses so much smaller? A proposal known as the seesaw mechanism offered a possible explanation. The idea emerged during the late 1970s through the work of several physicists, including Peter Minkowski, Murray Gell-Mann, Pierre Ramond, Richard Slansky, and Tsutomu Yanagida. The central concept is surprisingly simple when described in words. Instead of neutrinos having a single mass generated in the same way as electrons or quarks, the neutrino mass arises from an interaction between two components that exist on very different mass scales. One component corresponds to the familiar left-handed neutrino that participates in weak interactions. The other corresponds to a hypothetical right-handed neutrino that does not interact through the usual electroweak forces. This right-handed state could possess a mass enormously larger than any particle currently accessible in experiments. When the two states interact through the Higgs field that fills space, their coupling produces two effective neutrino masses. One becomes extremely heavy and essentially invisible at low energies. The other becomes extremely light. The effect resembles the balance of a physical seesaw on a playground. When one side becomes very heavy, the other rises correspondingly high. In particle physics, the heavy right-handed neutrino pushes the mass of the ordinary neutrino downward to an extraordinarily small value. This mechanism naturally explains why neutrinos weigh so little compared with other particles. Theoretical estimates illustrate how dramatic the scale difference could be. If the heavy partner possesses a mass near the scale where certain grand unified theories operate, around 10 to the power of 15 giga-electronvolts, the resulting light neutrino mass falls naturally within the range measured in oscillation experiments. This connection suggests that neutrino physics may offer a rare glimpse into processes occurring at energies far beyond the reach of current accelerators. The concept also introduces another intriguing possibility involving the nature of the neutrino itself. Many theories describing the seesaw mechanism treat the heavy right-handed neutrino as a Majorana particle. A Majorana particle differs from ordinary fermions because it is identical to its own antiparticle. The idea was first explored by the Italian physicist Ettore Majorana in 1937. In a Majorana description, the distinction between particle and antiparticle disappears for the neutrino. If neutrinos are Majorana particles, certain rare nuclear processes could occur in which two neutrons inside a nucleus transform into two protons and two electrons without emitting neutrinos. This process is called neutrinoless double beta decay. Detecting such an event would confirm that neutrinos are Majorana particles and would provide powerful evidence supporting the seesaw picture. Experiments searching for neutrinoless double beta decay are currently underway in laboratories deep underground where natural radioactivity is minimized. Detectors use large quantities of isotopes such as germanium-76 or xenon-136. Researchers monitor these materials for the distinctive energy signature that would indicate the simultaneous emission of two electrons without accompanying neutrinos. So far, no definitive observation has been reported, yet the sensitivity of these experiments continues to improve year by year. Beyond laboratory searches, cosmological observations also contribute valuable information about neutrino mass. Measurements of the cosmic microwave background radiation provide a snapshot of the universe approximately 380,000 years after the Big Bang. The European Space Agency Planck satellite mapped subtle temperature variations across the sky with remarkable precision. These variations carry information about the total mass of neutrinos because neutrinos influence how matter clumps together under gravity during cosmic evolution. Analyses of the Planck data indicate that the combined mass of all three neutrino types must remain below roughly 0.12 electronvolts. This constraint fits comfortably with the predictions emerging from neutrino oscillation experiments and from many theoretical models involving the seesaw mechanism. Astrophysical observations add further perspective. Neutrinos produced during supernova explosions escape from the collapsing core of a dying star long before light emerges. When supernova 1987A exploded in the Large Magellanic Cloud, detectors on Earth recorded a small burst of neutrinos several hours before the optical signal became visible. These neutrinos traveled across approximately 168,000 light-years of space before reaching Earth. Their arrival times and energies were consistent with extremely small neutrino masses. The remarkable journey of these particles demonstrates how neutrino physics connects laboratory experiments with cosmic events occurring across vast distances. Observations from underground detectors, space telescopes, and astrophysical phenomena all contribute pieces of the same puzzle. Carl Sagan once remarked that, "The cosmos is within us. We are made of star stuff." The neutrinos created in stellar reactions carry information from those distant processes directly into detectors on Earth. By studying their properties with increasing precision, physicists uncover clues about phenomena that may involve energies far beyond what terrestrial laboratories can achieve. The seesaw mechanism illustrates how a tiny mass observed today might be the consequence of an interaction with particles that existed at enormous energy scales in the earliest moments of the universe. If heavy right-handed neutrinos truly exist, they could have influenced the thermal history of the cosmos and may even have played a role in generating the imbalance between matter and antimatter observed today. That possibility leads naturally toward the next stage of the investigation. The weak interaction already distinguishes between left and right orientations of particles. If heavy neutrinos contributed to processes occurring in the early universe, their behavior might have helped establish the conditions that allowed matter to dominate over antimatter. And that realization prepares the ground for the next exploration titled, "Did this left-right imbalance help decide why matter won?" At the earliest moments after the birth of the universe, when temperatures exceeded trillions of degrees and particles collided with energies far beyond anything achievable in laboratories today, matter and antimatter should have existed in almost perfect balance. Yet, the observable universe today is filled overwhelmingly with matter. Galaxies, stars, planets, and living organisms all consist almost entirely of ordinary matter. Antimatter appears only rarely in cosmic rays or in the controlled environments of particle accelerators. The imbalance is unmistakable. If matter and antimatter had been created in exactly equal quantities during the earliest phases of cosmic evolution, they would have annihilated each other almost completely, leaving behind only radiation. The fact that any matter survived suggests that something in the laws of physics introduced a subtle preference during those early moments. Understanding how such a preference could arise became a major challenge in cosmology and particle physics. During the 1960s, the physicist Andrei Sakharov proposed a set of conditions required for a universe that begins with equal amounts of matter and antimatter to evolve into one dominated by matter. His proposal identified three necessary ingredients. The first involves processes that violate baryon number, meaning reactions that allow the total number of baryons such as protons and neutrons to change. The second involves violations of certain symmetries connecting particles and antiparticles. The third requires that these processes occur outside thermal equilibrium so that the imbalance can grow rather than cancel out. These requirements, now widely known as the Sakharov conditions, guide much of the research into the origin of matter. Each of them appears in various physical contexts, but the weak interaction provides a particularly interesting environment in which these ingredients can arise. The weak force already distinguishes between left and right orientations of particles, a feature revealed through the violation of mirror symmetry in the cobalt-60 experiment performed by Chien-Shiung Wu and collaborators during 1956. Mirror symmetry violation alone does not generate a matter-dominated universe. Another symmetry known as charge conjugation must also be broken. Charge conjugation refers to the transformation that replaces particles with their antiparticles. If this symmetry held perfectly, matter and antimatter would behave identically in every interaction. Experiments, however, show that certain processes governed by the weak interaction treat matter and antimatter slightly differently. The first clear evidence of this difference appeared in 1964 through experiments studying the behavior of neutral kaons. Physicists James Cronin and Val Fitch discovered that the decay patterns of these particles violated a combined symmetry involving both charge conjugation and mirror reflection. The phenomenon became known as charge parity violation. The discovery demonstrated that the laws of physics allow small differences between matter and antimatter in certain interactions. Further observations confirmed that charge parity violation occurs in other systems as well. Experiments studying particles known as B mesons at facilities such as the Bell experiment in Japan and the Barbar experiment in the United States measured similar asymmetries. These results established that the standard model includes mechanisms capable of producing slight differences in how matter and antimatter behave under the weak interaction. Despite these discoveries, the amount of asymmetry produced within the standard model appears too small to account fully for the enormous imbalance observed in the universe. Calculations indicate that the charge parity violation measured in known particle interactions would generate only a tiny excess of matter. Cosmological observations suggest that the universe contains roughly one extra matter particle for every billion matter-antimatter pairs created during the earliest stages of cosmic evolution. Although that ratio may seem small, it represents the crucial surplus that survived after nearly all matter and antimatter annihilated each other. Physicists therefore explore additional mechanisms that might amplify this asymmetry. One promising idea involves neutrinos and the possibility that heavy right-handed neutrinos existed in the early universe. In certain theoretical models, these heavy particles decay in ways that produce slightly more leptons than antileptons. Leptons are a family of particles that includes electrons and neutrinos. This imbalance among leptons could later be converted into an imbalance among baryons through processes allowed within the standard model. This scenario is known as leptogenesis. It connects the physics of neutrino mass with the cosmological origin of matter. The idea emerges naturally in theories where neutrino masses arise through the seesaw mechanism discussed earlier. In such models, heavy right-handed neutrinos could have existed shortly after the Big Bang when the universe was extremely hot and dense. As the universe expanded and cooled, these particles would have decayed into lighter particles, including ordinary neutrinos and Higgs bosons. If those decays favored leptons slightly over antileptons because of charge parity violation, the resulting imbalance could propagate through interactions that link lepton number and baryon number. Within the standard model, certain high-energy processes known as Phaleron transitions allow conversions between baryons and leptons while conserving a combined quantity. Through this pathway, a small initial lepton asymmetry could evolve into the baryon asymmetry observed today. The elegance of this picture lies in how several seemingly unrelated observations begin to connect. Neutrino oscillation experiments demonstrate that neutrinos possess mass. Theoretical models explaining those masses introduce heavy right-handed neutrinos. The decay of those particles in the early universe could produce the imbalance between matter and antimatter that allowed galaxies and stars to form. Evidence for this scenario remains indirect, yet cosmological measurements offer supporting clues. Observations of the cosmic microwave background radiation made by the Planck satellite of the European Space Agency provide detailed information about the composition of the universe. These measurements show that ordinary matter accounts for only a small fraction of the total cosmic energy density, yet the presence of matter rather than antimatter is unmistakable. Large-scale structures such as galaxy clusters also reveal that matter dominates the universe. If large regions of antimatter existed, Their boundaries with matter regions would produce intense gamma radiation from annihilation events. Astronomical observations have not detected such widespread signals, reinforcing the conclusion that the universe contains overwhelmingly more matter than antimatter. Particle accelerators continue to investigate the properties of neutrinos and other particles involved in these asymmetry-generating processes. Experiments such as the Tokai to Kamioka project in Japan and the Deep Underground Neutrino experiment in the United States aim to measure subtle differences in how neutrinos and antineutrinos oscillate. Detecting such differences would provide additional insight into the nature of charge parity violation in the neutrino sector. If neutrinos exhibit their own form of charge parity violation, the connection between neutrino physics and cosmic baryon asymmetry becomes even stronger. The behavior of these nearly invisible particles could hold the key to understanding why any matter survived the violent conditions of the early universe. Carl Sagan once noted that the universe is not required to be in perfect harmony with human ambition. The question of why matter exists in the abundance we observe reminds us that the universe evolved through processes governed by subtle asymmetries embedded within fundamental interactions. Each measurement of neutrino behavior, each observation of cosmic structure, contributes another piece to the larger puzzle. The investigation continues across laboratories and observatories around the world. Physicists analyze particle decays with extraordinary precision, while astronomers study the relic radiation left from the Big Bang. Together, these efforts seek to determine whether the asymmetry built into the weak interaction, combined with neutrino physics, played a decisive role in shaping the matter-filled cosmos. The exploration now approaches its final step. The journey began with a simple intuition that the universe might favor lower energy states. Along the way, we encountered deeper organizing principles involving symmetry, gauge structure, and the behavior of neutrinos. The remaining task is to gather these insights into a coherent answer about the origin of neutrino-handedness itself. That culmination unfolds in the concluding exploration titled, "So Why Are Neutrinos Left-Handed? What's the Most Honest Answer We Can Give Today?" When someone hears that neutrinos are always observed as left-handed, and immediately suggests that the universe must simply be choosing the most energy-efficient option, the careful answer from modern physics must begin by setting aside that intuition and returning to the structure of the laws themselves. The preference for left-handed neutrinos is not the result of a thermodynamic bargain, not a case of nature minimizing energy in the familiar sense used in chemistry or statistical mechanics. Instead, it reflects a property embedded in the weak interaction itself, a structural feature confirmed repeatedly in experiments since the middle of the 20th century. To understand the most honest answer available today, it helps to look back at how the discovery unfolded. In the early decades of nuclear physics, researchers studying radioactive decay noticed patterns that suggested a new force operating inside atomic nuclei. This force, later named the weak interaction, governs processes in which one type of particle transforms into another. A neutron can convert into a proton while emitting an electron and a neutrino. Such transformations occur constantly inside stars and in certain unstable isotopes on Earth. For many years, physicists believed that all fundamental interactions respected mirror symmetry. If a physical process were reflected as though in a mirror, the mirrored process should follow the same laws. This expectation seemed almost unavoidable because the equations describing electromagnetism and classical mechanics remained unchanged under such a reflection. The assumption held until the 1950s, when a careful re-examination of weak interaction data suggested that no direct experiment had ever tested whether mirror symmetry truly applied to beta decay. Sung-Dao Lee and Chen-Ning Yang proposed that the symmetry might fail for the weak force. Their proposal inspired an experimental test conducted by Chien-Shiung Wu and collaborators using cobalt-60 nuclei cooled to temperatures only a few thousandths of a degree above absolute zero. The nuclei were placed in a magnetic field so that their spins aligned in the same direction. As the nuclei decayed, detectors recorded the direction of emitted electrons. If mirror symmetry held, electrons would emerge equally in directions aligned with and opposite to the nuclear spin. The results revealed a clear asymmetry. The electrons were emitted preferentially in one direction relative to the spin orientation. The mirror version of the experiment would not behave the same way. This observation demonstrated that the weak interaction violates parity symmetry. In practical terms, it means that the weak force distinguishes between left and right orientations of particles. The discovery fundamentally changed the understanding of particle interactions. Further experiments soon revealed that neutrinos produced in weak processes possess a definite handedness. The neutrinos emitted in beta decay appear overwhelmingly with left-handed helicity, while antineutrinos appear with right-handed helicity. The pattern is not explained by energy optimization. Instead, it reflects the chiral structure of the weak interaction encoded in the standard model of particle physics. Within the electroweak theory developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg, the fundamental fields describing matter are organized according to a symmetry known as SU2 combined with another symmetry known as U1. The left chiral components of fermions appear in pairs under this structure. These pairs interact through the W boson, the particle responsible for charged current-weak interactions. Right chiral fermions occupy a different position in the theory. They do not belong to the same SU2 pairs and therefore do not couple to the W boson. Because neutrinos appear in these left chiral pairs, the weak interaction interacts only with that component. This is why neutrinos produced in weak processes consistently appear left-handed. The explanation becomes even clearer when considering the relationship between helicity and chirality. Helicity describes the alignment between a particle's spin and its direction of motion. Chirality describes how the particle's field transforms under the symmetries of space-time and the electroweak interaction. For particles with extremely small mass traveling close to the speed of light, the two properties almost coincide. Neutrinos fall into precisely that category. Experiments measuring neutrino oscillations show that neutrinos possess mass, but the masses are extraordinarily small, less than a fraction of an electron volt. When neutrinos carry energies millions of times larger than their mass, the state with the opposite helicity becomes extremely suppressed. As a result, neutrinos produced through the weak interaction appear almost entirely left-handed in experiments. This conclusion rests on decades of experimental evidence. Neutrino detectors buried underground, such as the Super Kamiokande Observatory in Japan and the Sudbury Neutrino Observatory in Canada, measure the behavior of neutrinos originating from the Sun and from cosmic ray interactions in Earth's atmosphere. These measurements confirm that neutrinos participate in the weak interaction exactly as predicted by the electroweak theory. Particle accelerators provide another testing ground. At the European Organization for Nuclear Research, high-energy proton collisions produce W bosons and other particles whose decay patterns reveal the chiral structure of the weak interaction. Detectors record the trajectories and energies of these particles with extraordinary precision. The results consistently support the conclusion that the weak force couples only to left chiral fermions. Astronomical observations also reinforce this understanding. Neutrinos produced during supernova explosions travel across vast distances before reaching Earth. The neutrinos detected from supernova 1987 are confirmed theoretical predictions about how these particles interact with matter through the weak force. Their behavior matches the same chiral interaction pattern measured in laboratory experiments. Even with this robust understanding, an important question remains open. The standard model includes left-handed neutrinos, but does not include right-handed neutrinos within its basic structure. The discovery that neutrinos possess mass suggests that additional components may exist. Many theoretical models propose the existence of right-handed neutrinos that do not interact through the weak force. Such particles would be extremely difficult to detect because they would lack the usual electroweak charges. They might interact only through gravity or through new interactions beyond the standard model. Some theories connect these particles with the origin of neutrino mass through mechanisms involving extremely heavy states. Others link them to processes that occurred during the earliest moments of cosmic history. The possibility remains under active investigation. Experiments searching for rare nuclear processes, known as neutrinoless double beta decay, aim to determine whether neutrinos behave as Majorana particles, identical to their own antiparticles. Observatories studying neutrino oscillations continue to measure subtle differences between neutrinos and antineutrinos that could reveal deeper properties of these particles. Each of these experiments contributes to the broader effort to understand why neutrinos possess the properties we observe today. The answer, currently supported by evidence, is clear in its main outline. Neutrinos appear left-handed because the weak interaction itself is chiral. The structure of the electroweak theory allows only left chiral fermions to participate in the interaction mediated by the W boson. At the same time, the story is not fully finished. The existence of right-handed neutrinos remains an open experimental possibility, connected to questions about the origin of neutrino mass and the behavior of matter during the earliest moments of the universe. The physicist Wolfgang Pauli, who originally proposed the neutrino in 1930 to explain missing energy in beta decay, later reflected on the strange asymmetry revealed by weak interactions. He once joked, "I cannot believe that God is a weak left-hander." The remark captured the surprise felt by physicists when they first realized that nature distinguishes between left and right at such a fundamental level. Today, that discovery stands as one of the defining insights of modern particle physics. It reminds us that the universe often reveals its structure through subtle asymmetries rather than through perfect balance. Thank you for spending this time exploring the remarkable story of neutrinos and the weak interaction. Your curiosity makes journeys like this possible. If these ideas have accompanied you quietly through the evening, I am grateful that you chose to listen and reflect along the way. May your thoughts now settle comfortably, your mind grow calm, and your rest tonight be deep and peaceful. Good night.